Welcome. In the previous video, we introduced generics and saw how to create functions that can take any type. In this video, we're going to discuss higher-order functions, their use cases, and their value proposition. We'll introduce the first of the higher-order functions that we'll be covering, which is filter. Finally, we'll add filter to our game of life. Our custom filter extension has quite a few use cases, but, as you may know, functionality like this has already been considered by the Swift team. In our previous exercise, we've essentially re-implemented Swift's filter function. While the functionality of filter is similar to Swift's, our filter is not a perfect copy. Swift's filter looks more like this. You see that it has the ability to throw exceptions and uses a while loop with a generator rather than a for loop like ours. Swift's filter is safer, while ours can be a bit faster. Filter is a higher-order function that is common in many programming languages. Higher-order functions are functions that accept another function as an argument and can also return functions. Although higher-order functions can make for relatively terse code, there's also an underlying goal. And it isn't just to save some characters. The idea is to get to the point quicker, to make readable code while doing away with much of the ceremonial boilerplate code that can hinder clarity. One of the big selling points to higher-order functions is when we chain multiple functions together, which we'll see later in this section. As a disclaimer, I should point out that there usually isn't a performance benefit to switching your looping logic for higher-order functions. Keep in mind that higher-order functions are just abstractions of commonplace programming solutions under the hood, so the performance will usually be on par with the logic you're replacing. We'll be sure to do some measurements between some higher-order functions and their lower-level counterparts in Section 7, Performance Optimization and Intro to Algorithms. Let's return to the definition of Swift's filter function to begin our deconstruction of higher-order functions. This may look a bit daunting at first, but we can break it down piece by piece to understand it better. Adding @noEscape guarantees that the closure will not be used asynchronously, used at a later time, or stored. The type of the include element parameter is a closure that takes a generator element and returns a bool. We'll be taking a closer look at generators later in this section. For now, just know that a generator is something that can give you the next element in a sequence of elements. We see that filter has the ability to throw and rethrow exceptions, something we'll get into in Section 6, Troubleshooting, Advanced Debugging, and Error Handling. The return type of filter is also an array of the same type as the argument to its closure, generator element. What this means is that the resulting array will be an array of objects of the same type as the parameter array. The logic inside of Swift's filter should be somewhat familiar. One thing to notice is that Swift uses a contiguous array rather than a simple array. Contiguous arrays are much like array, except they can be faster in some cases. However, they lack the ability to bridge to Objective-C. Then we have another generator and a while loop that does close to what we've done in our custom filter implementation. So, in short, Swift's filter method takes a function which, given an element in the array, returns a bool indicating whether the element should be included in the resulting array. Let's make some progress in our application by putting Swift's filter to work. So we've got the functionality to determine the neighbors for our cells. Now we need to add a way to determine which one of our cell neighbors are living. We'll add another function to our class called living neighbors. We see that this function takes a cell and passes it to our cell's neighbor array. Recall that our cell's neighbor array returns an array of cell. Since we know that the return of this function is an array of cell, we can simply chain Swift's filter function to it, which will check each item in our array to see if it has a state equal to living. Of course, we can always simplify our closures by utilizing an implicitly named variable, which will reduce our filter statement to just one line. This is an excellent example of functional programming at work. Now that we have a way to determine the neighbors of a cell and whether a cell's neighbors are living or not, we can employ the rules of game of life. In our evolve method, let's utilize filter to find all of the living cells and all of the dead cells. These are simple operations that compare the cell state to the state that we're filtering for. Next, we'll implement rules 1, 2, and 3 in one call. Here, our filter is looking for live cells with fewer than 2 live neighbors, and cells with more than 3 live neighbors, while filtering out cells that have 2 or 3 living neighbors, which, as a rule state, will live on to the next generation. And finally, we implement Rule 4. Any dead cell with exactly 3 live cells becomes a live cell again. Now that we've sorted out which of our cells live and which of our cells die, we need to update our states and display them on our game board. For now, let's just employ 2 simple loops. We'll loop over our new live cells and set their states to living. We'll loop over our dying cells and set their states to dead. Before we can run our game, we'll need to make some changes to our view controller. We'll need to add a way to set our game in motion. We'll do this by adding a tap gesture recognizer on our grid that will start a timer when tapped. At the bottom of our viewDidLoad, we'll define a variable named tap and assign a value of UI tap gesture recognizer with a target of self and an action of start timer. Then we'll add our gesture recognizer to our board view. Now, whenever our game board is tapped, our start timer function will fire. Let's continue by adding our start timer function to our view controller class. This function takes a UI gesture recognizer as an argument, though we won't be using it here. At the top of the view controller, create a variable named timer. We'll put this timer to use inside of our start timer function. We'll set our timer variable's value to nstimer.scheduleTimer with time interval. We'll set it to evolve every 5/100ths of a second, set its target to self, selector to moment, user info to nil, and set repeats to true. Next, let's add a method called initializeGame, which will randomize our cell states. This method will come in handy for when we want to start a new game. We see this method has a for-in loop that loops over each item in the life.cells array and utilizes our stateEnums mutating function to randomly select states. Let's open up our main.storyboard and add a button to our view, which we'll name Reset. We'll open up the Assistant Editor and drag an action from our new Reset button to our view controller. Make sure you select Action and name your new action Handle Reset Button Tapped. Then, inside the Reset Button action, we'll call timer.invalidate, which stops and invalidates our timer. Then we'll call initializeGame, which gives us a fresh game board, and then we'll call gameboard.setNeedsDisplay, which redraws our game board. Finally, let's create the method we specified in our NSTimer, named Moment. We'll call life.evolve and redraw our game board each time our NSTimer fires. Build and run, and you should see your cells come to life. In this video, we explored higher-order functions and discussed their value proposition. We also looked at and employed our first higher-order function. In the next video, we'll continue with our higher-order function dialog and discuss Swift's map function.